In this lecture, we are going to derive the system of equations for finding the cubic spline curve that passes through a given finite number of points. The cubic spline will not be a polygonal path, but will be a smooth curve. We construct the cubic spline by piecing together different polynomial curves between consecutive points. We arrange the x-coordinates of the different points or nodes in increasing order from x sub 0 through x sub n. And so between consecutive x-coordinates x sub k and x sub k plus 1, we have the polynomial p sub k of x, k going from 0 through n minus 1. As the term cubic spline suggests, each p sub k is a cubic polynomial. P sub k of x is equal to a sub k times the cube of the quantity x minus x sub k plus b sub k times the square of the quantity x minus x sub k plus c sub k times the quantity x minus x sub k, and the last term is d sub k. Our goal is to come up with a system of equations by using the second derivatives so that we can find a sub k, b sub k, c sub k, and d sub k. The first thing that we should do is to make sure that the cubic spline passes through the different nodes. We plug in x sub k in p sub k of x. And find that p sub k of x sub k is equal to d sub k. But p sub k of x sub k is equal to y sub k. And so d sub k equals y sub k. We now find formulations for a sub k, b sub k, and c sub k in terms of the second derivative values at the nodes. We define the new variable uppercase s sub k as the second derivative value of p sub k at x sub k. As an easy calculus exercise, we find that the second derivative of p sub k of x is equal to 6a sub k times the quantity x minus x sub k plus 2b sub k. And so p sub k double prime of x sub k is equal to 2b sub k. And so s sub k equals 2b sub k. Therefore, b sub k equals s sub k divided by 2. To find a sub k in terms of the s sub k's, we take a look at the second derivative value at x sub k plus 1. Because this is the second derivative value at x sub k plus 1, this is also equal to s sub k plus 1. We plug in x sub k plus 1 in p sub k double prime and get this formulation for p sub k double prime of x sub k plus 1. We introduce a new variable h sub k, which will be equal to x sub k plus 1 minus x sub k. And so p sub k double prime of x sub k plus 1 is equal to 6a sub k times h sub k plus 2b sub k. Now 2b sub k is equal to s sub k, and p sub k double prime of x sub k plus 1 is equal to s sub k plus 1. And so we can solve for a sub k in terms of s sub k plus 1 and s sub k, and find that a sub k is equal to s sub k plus 1 minus s sub k all over 6 times h sub k. To get the formulation for c sub k in terms of s sub k, we use the equation that we refer to as the continuity equation. All this equation says is that the cubic spline must be continuous. This implies that consecutive polynomial segments must meet at the common node. For example, p sub k of x sub k plus 1 must equal p sub k plus 1 of x sub k plus 1. For the left side of the equation, we plug in x sub k plus 1 into p sub k of x. Now the y value at x sub k plus 1 is supposed to be y sub k plus 1. And y sub k plus 1 equals d sub k plus 1. So d sub k plus 1 completes the equation. Recall that we had defined h sub k to be equal to x sub k plus 1 minus x sub k. So we are able to transform this last equation into an equation involving h sub k. Since the last polynomial segment is p sub n minus 1, d sub k goes only all the way up to d sub n minus 1. So for this last equation, k goes from 0 through n minus 2. We now use these formulas to transform the last equation into an equation involving the s sub k's. Using the formula for a sub k, we transform the first term. We then use the formula for b sub k to transform the second term. We don't have a formula for c sub k, and so the third term stays as is. Now d sub k is y sub k, and d sub k plus 1 is y sub k plus 1. So y sub k and y sub k plus 1 complete the next equation. Now the y values go from y sub 0 through y sub n. And so for this last equation, k goes from 0 through n minus 1. We simplify this last equation and we get this next equation. First, we have the term involving the second derivatives, followed by the c sub k term, and then we have y sub k on the left side and y sub k plus 1 on the right. Finally, we get to solve for c sub k, and c sub k is given by this formula. In deriving the formulas that we have on the right, we did not use the first derivative of the polynomial segments. And so to find the system of equations involving the s sub k's, we use p sub k prime. As a very elementary calculus exercise, one should be able to find that p sub k prime of x is equal to 3a sub k times the square of the quantity x minus x sub k plus 2b sub k times the quantity x minus x sub k plus c sub k. For the left node, we plug in x sub k for x in p sub k prime, and find that p sub k prime of x sub k equals c sub k. At the right node, when x is equal to x sub k plus 1, p sub k prime of x sub k plus 1 equals 3a sub k times the square of x sub k plus 1 minus x sub k plus 2b sub k times the quantity x sub k plus 1 minus x sub k plus c sub k. Since x sub k plus 1 is the x-coordinate of the shared node between p sub k and p sub k plus 1, p sub k prime of x sub k plus 1 should equal p sub k plus 1 prime of x sub k plus 1. And according to this equation, p sub k plus 1 prime of x sub k plus 1 should equal c sub k plus 1. We replace x sub k plus 1 minus x sub k by h sub k, and obtain this expression involving h sub k for p sub k prime of x sub k plus 1. This is still equal to p sub k plus 1 prime of x sub k plus 1, and so it is equal to c sub k plus 1. All we have to do now is to use these formulas and replace a sub k, b sub k, c sub k, and c sub k plus 1 to get an equation involving the s sub k's. The first term on the left side is 3 times s sub k plus 1 minus s sub k all over 6h sub k times the square of h sub k. The term 2b sub k h sub k is replaced by the simple term s sub k h sub k. We complete the left side by replacing c sub k using this formula. We use the exact same formula for c sub k plus 1, but this time we increase the subscripts by 1. This last equation in itself is an equation that we can actually use for our system of equations, but we will rewrite this equation. We write the terms individually involving s sub k plus 1, and s sub k plus 2. The first term on the left, where we combine all the terms involving s sub k, should be s sub k times h sub k divided by 6. The term involving s sub k plus 1 should be 2 times s sub k plus 1 times the quantity h sub k plus h sub k plus 1 divided by 6. And the term involving s sub k plus 2 is s sub k plus 2 times h sub k plus 1 divided by 6. For the right side, we simply bring the terms that do not involve the s sub k's. We multiply everything by 6 to get a slightly neater form of the equations. What we have here is a total of n-1 equations. However, unfortunately for us, the unknowns s sub 0 through s sub n constitute n plus 1 unknowns, and so we are missing 2 equations. The 2 missing equations can be supplied by the user, and they can depend on the phenomenon for which the cubic spline is being used. We illustrate 2 types of cubic splines and show how the 2 missing equations can be supplied. The first type of cubic spline is that of a natural spline. The second type is a clamped spline. The natural spline is rather easy. All it says is that the second derivative values at the leftmost and the rightmost endpoints are both equal to 0. And so the 2 missing equations are s sub 0, which is the second derivative value at the left endpoint, is equal to 0. And s sub n, which is the second derivative value at the rightmost endpoint, this is also equal to 0. And these 2 equations complete the system of equations for the natural spline. For the clamped spline, we specify the values of the slopes at the leftmost and the rightmost endpoints. Suppose that the slope at the leftmost endpoint is slope sub 0. Then the slope at the first polynomial segment p sub 0 should be equal to slope sub 0. And so the equation should be p sub 0 prime of x sub 0 equals slope sub 0. And if the slope at the rightmost endpoint is specified to be slope sub n, then we get a similar equation. This time it's p sub n minus 1 prime of x sub n equals slope sub n. We still have to convert these 2 equations into equations involving the s sub k's, because after all, these 2 equations are supposed to become part of the system of equations for solving for the s sub k's as unknowns. Recall one of the equations that we found earlier on, that is p sub k prime of x sub k is equal to c sub k. And so replacing k by 0, p sub 0 prime of x sub 0 equals c sub 0, and therefore c sub 0 equals slope sub 0. We then use this equation and replace k by 0, and we get y sub 1 minus y sub 0 all over h sub 0, minus s sub 1 plus 2s sub 0 all over 6 times h sub 0 equals slope sub 0. To convert this other equation into something in terms of s sub k, we recall that p sub k prime of x is equal to 3a sub k times the square of x minus x sub k plus 2b sub k times the quantity x minus x sub k plus c sub k. First, we replace k by n minus 1, and then plug in x sub n for x, and we get this expression for p sub n minus 1 prime of x sub n. We again use these formulas to transform a sub n minus 1, b sub n minus 1, and c sub n minus 1 by what they are in terms of S sub n and S sub n minus 1. We will also replace x sub n minus x sub n minus 1 by h sub n minus 1. And this is the expression that we get. And don't forget, this is supposed to be equal to slope sub n. We keep the terms that involve S sub n and S sub n minus 1 on the left side, and everything else we bring to the other side. With a little simplification, this is the equation that we get. Multiplying by 6, we get the final form for the last equation to complete the system for the clamped spline.